Welcome! In this session, we will explore LeetCode problem number 2155, all divisions with the highest score of a binary array. This is a fascinating problem that challenges us to think critically about arrays and scoring mechanisms. We'll dive into various approaches to solve it efficiently. Let's get started. This problem is about finding the best way to divide a binary array to maximize a specific score. The binary array, called nums, contains only zeros and ones, and it has a length of n. A division is defined by an index I such that the array is split into two parts, the left part, which includes all elements before the index I, and the right part, which includes all elements from the index onward. The score for each division is calculated as the sum of two components, the number of zeros in the left part and the number of ones in the right part. The goal is to find all indices that yield the highest score. We need to return these indices as a list, and the order of indices in the output doesn't matter. The input to this problem is a binary array, meaning it contains only the integers 0 or 1. The output is a list of all the indices that result in the highest score. Let's look at an example. Suppose the input array is 0, 0, 1, 0. We calculate the score for each possible division. For I equals 0, the left part is empty, so it has number zeros, and the right part is the entire array, 0, 0, 1, 0, which has 1, 1. This gives a score of 0 plus 1 equals 1. For I equals 1, the left part is 0, with 1, 0, and the right part is 0, 1, 0, which has 1, 1. The score here is 1 plus 1 equals 2. For the same example, when dividing at I equals 2, the left part becomes 0, 0, with 2 zeros, and the right part is 1, 0, with 1, 1. This results in a score of 2 plus 1 equals 3. At I equals 3, the left part is 0, 0, 1, with 2 zeros, and the right part is 0, with number ones, giving a score of 2 plus 0 equals 2. Finally, at I equals 4, the left part includes the entire array, 0, 0, 1, 0, with 3 zeros, and the right part is empty, contributing number ones. The score here is 3 plus 0 equals 3. The highest score is 3, which occurs at indices 2 and 4. Therefore, the output is 2, 4. Now consider another example where the input array is 0, 0, 0. Here, at I equals 0, the left part is empty, and the right part is the entire array, 0, 0, 0. Since there are number ones in the right part, the score is 0 plus 0 equals 0. At I equals 1, the left part is 0, with 1 0, and the right part is 0, 0, with number ones, giving a score of 1 plus 0 equals 1. At I equals 2, the left part is 0, 0, with 2 zeros, and the right part is 0, with number ones, resulting in a score of 2 plus 0 equals 2. Finally, at I equals 3, the left part is 0, 0, 0, with 3 zeros, and the right part is empty, giving a score of 3 plus 0 equals 3. The highest score is 3, which occurs only at index 3, so the output is 3. Let's look at one more example where the input array is 1, 1. For I equals 0, the left part is empty, and the right part is 1, 1. Since the right part has two ones, the score is 0 plus 2 equals 2. For I equals 1, the left part is 1, with number zeros, and the right part is 1, with 1, 1, resulting in a score of 0 plus 1 equals 1. Finally, for I equals 2, the left part is 1, 1, with number zeros, and the right part is empty, giving a score of 0 plus 0 equals 0. The highest score is 2, which occurs only at index 0. Thus, the output is 0. There are a few edge cases to keep in mind when solving this problem. First, if all elements in the array are 0, the highest score will depend entirely on the number of zeros in the left part, since the right part contributes nothing. Conversely, if all elements are 1, the score depends on the number of ones in the right part. For a single element array, there is only one possible division, where the left part is empty and the right part is the entire array. Finally, in cases where the array alternates between 0 and 1, the scores will vary depending on the balance of zeros and ones in the left and right parts, which can make the computation more dynamic. To solve the problem of finding all divisions with the highest score of a binary array, we need to identify indices that maximize the score. The score is defined as the count of zeros in the left part of the array and the count of ones in the right part. A straightforward way to approach this is with a brute force method. Here, for each possible division index, we calculate the score by counting zeros in the left segment and ones in the right segment. While this is intuitive and easy to implement, the downside is its inefficiency. Since we recalculate counts for every division, the time complexity becomes n squared, which is computationally expensive for larger arrays. This makes the brute force approach impractical for large inputs, prompting us to look for optimizations. To improve efficiency, we can use an optimized approach based on prefix sums. The idea here is to pre-compute cumulative counts of zeros and ones, which allows us to calculate the score for any division index in constant time. Specifically, we define two prefix arrays, one for zeros and another for ones. The score for any division index can then be computed as the sum of zeros in the left part and ones in the right part, derived directly from the prefix arrays. With this setup, we only need a single pass to compute the prefix sums, and another pass to evaluate scores for all possible divisions. This reduces the time complexity to n, making it much faster than the brute force method. However, we do require additional memory to store the prefix arrays, which could be a consideration for extremely large inputs. To further optimize, we can eliminate the need for prefix arrays by using a single pass approach with two counters. Here, we dynamically track the count of zeros in the left part and ones in the right part as we iterate through the array. We start by initializing the left 0 count to 0 and the right 1 count to the total number of ones in the array. As we process each element, we update these counters based on whether the current element is a 0 or a 1, and compute the score for the current division index. This approach not only retains the n time complexity but also reduces space usage to 1, since we no longer need additional memory for prefix arrays. This makes it the most efficient solution in terms of both time and space. The efficiency of the single-pass approach stems from a key observation: the score can be broken down into two independent components, left zeros and right ones, both of which can be updated dynamically. This eliminates the need for redundant calculations, making it highly efficient. While the brute force approach is simple to understand, it is computationally expensive. The prefix sum method offers a middle ground with better efficiency but requires extra memory. The single pass approach, on the other hand, achieves the best balance by being both time and space efficient. It is particularly well suited for large inputs, as it avoids unnecessary computations and memory overhead. This makes it the most robust and scalable solution to the problem. The goal of this problem is to find all indices in a binary array where dividing the array into two parts results in the highest score. The score at any division index is calculated as the sum of zeros in the left partition and ones in the right partition. To solve this efficiently, the first step is to pre-compute the prefix and suffix counts. Specifically, we need the cumulative count of zeros in the left part and the cumulative count of ones in the right part for each index. To achieve this, we can use two separate passes through the array. First, we calculate the prefix 0 count by iterating from left to right and maintaining a running total of zeros. This is stored in an array where each element represents the number of zeros up to that index. Similarly, we calculate the suffix 1 count by iterating from right to left and maintaining a running total of ones, storing these values in another array. By pre-computing these counts, we set up the foundation for efficiently calculating the scores at each division point. Once the prefix 0 counts and suffix 1 counts are pre-computed, we can calculate the score for each division index using a simple formula. The score at index I is the sum of the prefix 0 count at I and the suffix 1 count at I. At the boundaries, the score simplifies. For example, at I equals 0, the left part is empty, so the score is just the total number of ones in the entire array. Similarly, at I equals n, the right part is empty, so the score is the total number of zeros in the entire array. After defining this scoring formula, we iterate through all possible indices, compute the score for each one using the pre-computed counts, and store these scores in an array. The next step is to determine the maximum score among these values. This can be done in a single pass through the score array. Finally, we collect all indices where the score equals the maximum score. This involves a second pass through the score array to filter and store the indices where the maximum score occurs. Pre-computing the prefix and suffix counts is a critical optimization in this approach. Without it, we would need to recompute the counts for every division point, resulting in a time complexity of n squared. Instead, with pre-computation, we achieve an overall time complexity of O(n) for these calculations. Additionally, we need to consider edge cases. If the array is empty, no divisions are possible, so the result should be 0. If the array contains only zeros or only ones, we handle these cases explicitly to avoid unnecessary computations. In terms of traversal, we use 2 passes to compute the prefix and suffix counts, followed by 2 additional passes to calculate the scores and collect the result indices. This ensures that our solution remains efficient and scalable. To store the cumulative counts, we use 2 auxiliary arrays, one for the prefix 0 count and another for the suffix 1 count. These arrays enable constant time access to the pre-computed values during score calculation. For storing the result indices, we use a simple list. The time complexity of this solution is O(n). This includes O(n) for pre-computing the prefix and suffix counts, O(n) for calculating the scores, and O(n) for collecting the indices with the maximum score. The space complexity is also O(n), which comes from the additional arrays used for storing the prefix 0 counts, suffix 1 counts, and the result indices. Overall, this algorithm is optimized to handle the problem efficiently, leveraging pre-computation and systematic traversal to achieve linear time complexity while maintaining clarity and simplicity in its implementation. Here, we are implementing the solution to find all the division indices in a binary array that yield the highest score. We start by defining the maxScore indices method inside the solution class. The first step is to calculate the total number of ones in the input array, nums, using the sum function. This helps us keep track of how many ones are present in the entire array, which will be useful as we iterate. Next, we initialize several variables, left_zeros to count the zeros on the left side of a division, right_ones to represent the count of ones on the right side, initially set to total_ones, max_score to track the highest score encountered so far, and result, which will store all indices that achieve this maximum score. The main logic involves iterating over all possible division points in the array, including index n, which represents dividing after the last element. For each division point, we calculate the score by adding the count of zeros on the left to the count of ones on the right. If this score exceeds the current max_score, we update max_score and reset the result list to just the current index. If the score is equal to max_score, we simply append the index to the result list. Finally, we prepare for the next iteration by updating the left_zeros and right_ones counts based on the value at the current index, but only if we haven't reached the last division point. To update the counts for the next division point, we check the value of the current element in nums. If the element is 0, it means we're adding another 0 to the left side of the division, so we increment left_zeros by 1. Otherwise, if the element is 1, we decrement right_ones, since 1 less 1 will remain on the right side after this division. Once we've completed iterating through all possible division points, we return the result, which contains all the indices where the highest score was achieved. This approach ensures that we efficiently calculate the scores in a single pass, maintaining an optimal time complexity. By carefully updating the counts of zeros and ones as we iterate, we avoid redundant calculations and produce the correct result. Here, we start by importing the necessary libraries and defining our solution class. The main method we are implementing is maxScore indices, which takes an integer array nums as input. This array represents the binary array we need to process. First, we determine the total number of ones in the array using a simple loop to sum up all the elements. This is stored in the variable total_ones. Next, we initialize 3 key variables, left_zeros, which keeps track of the number of zeros to the left of the current division, right_ones, which starts as total_ones and represents the number of ones to the right of the division, and maxScore, which tracks the highest score we encounter as we iterate through the array. We also initialize a result list to store the indices where the maximum score occurs. The main logic involves iterating over all possible division points from 0 to n, where n is the length of the array. For each division, we calculate the score as the sum of left_zeros and right_ones. If this score is greater than the current max score, we update maxScore and clear the result list to start fresh, as this is now the new highest score. If the score at the current division matches the max score, we simply add the current index to the result list. This ensures that we are collecting all indices where the maximum score occurs.
After processing the score for the current division, we update the left zeros and right ones variables to reflect the next division point.
If the current element in nums is 0, we increment left zeros, as there is now one more 0 to the left of the division. Otherwise, if the current element is 1, we decrement right ones, as there is now one less 1 to the right of the division. This process continues until all possible divisions have been evaluated. Finally, we return the result list, which contains all the indices where the maximum score is achieved. This implementation ensures an efficient computation of the desired result by leveraging pre-computation and careful updates of the score components. Here we start with the example array nums equals 0, 0, 1, 0. The length of the array, n, is 4, and the total number of ones in the array is 1. We initialize several variables, left underscore zeros is 0 to track the count of zeros on the left of the division, and right underscore ones is 1, which matches the total number of ones initially since no ones have been removed from the right side yet. We also set max underscore score to 0 and initialize an empty list result to store the indices that yield the highest score. As we iterate through possible division indices, the score is calculated as the sum of left underscore zeros and right underscore ones. In the first iteration, at index I equals 0, the score is 0 plus 1 equals 1, so we update max underscore score to 1 and add 0 to the result. No updates to left underscore zeros or right underscore ones are needed yet. For the second iteration, I equals 1, we process nums, 0 equals 0, so left underscore zeros increases to 1 while right underscore ones remains 1. The score becomes 1 plus 1 equals 2, which updates max underscore score to 2, and the result is updated to 1. In the third iteration, when I equals 2, we process nums, 1 equals 0, so left underscore zeros increases to 2, and right underscore ones remains 1. The score is calculated as 2 plus 1 equals 3, which updates max underscore score to 3, and the result is updated to 2. For iteration 4 at I equals 3, nums, 2, equals 1 is processed, so left underscore 0 stays at 2, but right underscore ones decreases to 0 as the 1 at this index is now part of the left side. The score becomes 2 plus 0 equals 2, which does not exceed the current max underscore score of 3, so no updates are made to the result. Finally, in the fifth iteration, I equals 4, processing nums, 3, equals 0 increases left underscore zeros to 3 while right underscore 1 stays at 0. The score is 3 plus 0 equals 3, which matches the max underscore score. Therefore, we add 4 to the result, making it 2, 4. The final output for this example is 2, 4. Now let's consider the second example, where nums equals 1, 1, 1. The array length n is 3, and the total ones in the array, total underscore ones, is 3. We initialize the same variables, left underscore zeros equals 0, right underscore ones equals 3, max underscore score equals 0, and an empty result list. For the first division index, I equals 0, the score is calculated as left underscore zeros plus right underscore ones equals 0 plus 3 equals 3. This updates max underscore score to 3, and we add 0 to the result. In the second iteration, I equals 1, processing nums, 0, equals 1 keeps left underscore zeros at 0 but decreases right underscore ones to 2. The score becomes 0 plus 2 equals 2, which does not exceed the current max underscore score, so there are no changes to the result. For the third iteration, I equals 2, processing nums, 1 equals 1 keeps left underscore zeros at 0 while reducing right underscore ones to 1. The score is 0 plus 1 equals 1, which is still less than the current max underscore score. Finally, in the fourth iteration, I equals 3, processing nums, 2, equals 1 keeps left underscore zeros at 0 and decreases right underscore ones to 0. The score is 0 plus 0 equals 0, which again does not exceed the max underscore score. Therefore, the result remains 0, which is the final output for this example. For the third example, nums equals 0, 1, 0, 1, 0, we would follow the same step-by-step process of iterating through all indices, updating left underscore zeros, right underscore ones, and calculating the score to identify the indices yielding the highest score. The final output for this case is 2, 4. To analyze the time complexity of the solution, we start with the pre-computation step. Calculating the total number of ones in the array using the sum function takes n time, where n is the length of the array. Next, we have the iteration through all possible divisions of the array. This loop runs for n+1 iterations since we evaluate divisions at every index, including before the first and after the last element. Within each iteration, the operations are efficient in constant time, computing the score by summing left_zeros and right_ones is 0, 1, updating the maximum score and appending to the result list is also 0, 1 on average, and updating the cumulative counts of zeros and ones is similarly 0, 1. Therefore, the total time for the loop is n+1, which simplifies to n. These two steps together dominate the overall time complexity, so the solution has a time complexity of n. Returning the result list has a time complexity of k, where k represents the number of indices with the highest score. In the worst case, all indices might have the same score, meaning k could be as large as n+1. However, this cost is already accounted for during the iterations since appending to the list happens within the loop itself. When we combine the time for pre-computing total_ones and iterating through the array, the dominant term remains n. Thus, the overall time complexity of the solution is n. Now, looking at the space complexity, the algorithm utilizes a constant amount of space for variables such as left_zeros, right_ones, max_score, and total_ones, all of which take up 1 space. The result list, however, grows based on the number of indices with the highest score. In the worst case, this list will store n+1 indices, which requires n space. Additionally, the algorithm does not rely on any auxiliary data structures apart from the result list. All calculations, such as updating cumulative counts and computing scores, are performed in place using the given variables. This means no extra arrays or significant memory allocations are required. As a result, the overall space complexity of the algorithm is determined by the result list, which is n. Comparing this to a brute force approach, the naive method would involve repeatedly iterating over the array to count zeros and ones for each division. This would require nested loops, leading to a time complexity of n squared. The space complexity in the brute force approach would still be n, due to the need to store result indices. In contrast, the current optimized algorithm eliminates redundant computations by maintaining cumulative counts for zeros and ones. This reduces the time complexity to n, while keeping the space complexity at n. Now, considering the best and worst case scenarios, the algorithm's time complexity always remains n, because the main loop iterates over all indices regardless of the input. The result list size may vary, but in the worst case, it could grow to n if all divisions yield the same score. The key advantage of the optimized algorithm lies in its efficiency. Compared to the brute force approach, which has a time complexity of n squared, this solution is significantly faster, making it suitable for large input sizes. While both approaches have the same space complexity of n, the optimized algorithm minimizes unnecessary computations and achieves its results more efficiently. In conclusion, the optimized solution strikes a balance between time and space, providing a practical and scalable approach to solving the problem. When solving this problem, there are a few common mistakes you'll want to avoid. First, it's easy to miscalculate the number of ones or zeros in the prefix or suffix while iterating through the array. This often happens if you update the counts at the wrong index or fail to initialize them properly. Always make sure your prefix and suffix counters are in sync with the current iteration. Another pitfall is forgetting to test edge cases. For instance, if the array contains all zeros or all ones, the highest score might occur at the very first or very last index. Testing special cases like an empty array is critical to ensuring correctness. Some users also attempt a brute force approach by calculating the score at every division point using nested loops. While this might seem intuitive initially, it leads to an inefficient in superscript 2 complexity, which is impractical for large arrays. Instead, you should aim for optimization using prefix sums. Lastly, be wary of off-by-one indexing errors. Since the score requires dividing the array into two parts at each index, it's easy to accidentally include or exclude elements. Always double-check your indexing logic to avoid such issues. Another common mistake is not handling cases where multiple indices yield the maximum score. The problem explicitly requires returning all such indices, but some solutions stop after finding just one. To address this, you need to maintain a list of all indices that achieve the highest score. From an interview perspective, this problem is designed to evaluate your ability to optimize computations, specifically, your use of prefix sums or cumulative counts to reduce redundant calculations. Clear communication is key, so practice explaining the intuition behind these optimizations, such as how prefix sums avoid recalculating values repeatedly. Be ready to discuss edge cases, like arrays of all zeros or all ones, and demonstrate how your solution handles them.
Additionally, interviewers may assess your debugging skills.
Mention strategies like using print statements or crafting specific test cases to verify your prefix and suffix computations. Finally, you might be asked to explore alternative approaches or extensions, such as modifying the array or introducing weighted scores. Be prepared to brainstorm and think creatively about these variations.
This problem shares concepts with several related problems that are worth exploring.
For instance, LeetCode 1423, maximum points you can obtain from cards, involves a similar prefix and suffix logic to maximize a score. LeetCode 724, find pivot index, requires balancing prefix and suffix sums, making it another great example to study. Similarly, LeetCode 1991, find the middle index in array, also focuses on achieving balance between prefix and suffix sums. For a more advanced challenge, LeetCode 862, shortest subarray with sum at least k, uses prefix sums in a slightly different context, emphasizing optimized computation. These problems not only reinforce the core prefix-suffix technique but also expose you to variations in applying this concept, helping you build a deeper understanding that can be useful in interviews.
There are several approaches you can consider when solving this problem. The brute force method involves calculating the score for every division point using nested loops. While this approach is straightforward to implement, its O(n) superscript 2 complexity makes it unsuitable for larger input sizes. A more efficient approach is to use optimized prefix and suffix counts.
By maintaining running totals of ones and zeros, you can compute scores in O(n) without redundant calculations. However, this method requires careful initialization and debugging of your counters. Alternatively, you can use the sliding window technique, which is conceptually similar to prefix sums but involves maintaining a dynamic window of ones and zeros as you iterate. For some, this approach may be easier to debug while still offering O(n) performance. Lastly, in special cases where the array is sorted or has certain properties, binary search can be used to optimize the process of finding division points. While this method is less general, it's highly efficient for specific scenarios and is worth exploring as part of follow-up discussions.
Great job! We've covered the key aspects of solving problem number 2155, focusing on efficient algorithms and takeaways. Remember to practice similar problems to build your skills. Thank you for joining, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!